Security Applications Engineer at Tortuga Logic. I will start with an introduction to hardware security and vulnerabilities, and then present the different components of the security methodology. I will also introduce the technology behind Tortuga Logic's Radix tool and how it fits into the hardware verification flow. My colleague Jagadish Nayak will then show a demo of applying the methodology and Radix on an SoC example. There's been an exponential growth in hardware security vulnerabilities over the last decade, as reported in the National Vulnerability Database. The increased number of vulnerabilities is due to, first, security being implemented directly in hardware, for example, through hardware root of trust and secure architectures such as Arm's Trust Zone. While implementing security functions in hardware generally makes the system more secure, mistakes in architecture or implementation can introduce severe vulnerabilities. Second, growing design complexity and interaction between security hardware and firmware. This makes system-level security verification challenging. And thirdly, architectural vulnerabilities allows remote exploits. This leads to a dramatic increase in attack surface and the number of systems being vulnerable. Hardware security verification is critical because hardware vulnerabilities can't be fixed after the product is shipped. Traditional hardware hacking analyzes physical effects through direct measurements or inserting faults through, for example, clock glitching or laser beams, and it requires physical access to the device. This usually has limited business impact since it only affects one device and it's difficult to scale. Recent attacks such as Spectre and Meltdown are much scarier. They utilize logical or architectural side effects in the design, and they can be done remotely from anywhere in the world. The business impact can be huge since the attacks are repeatable and scalable and attack all devices with the specific vulnerabilities. Hence, focusing on preventing these types of vulnerabilities have the highest return on investment. Security is conventionally viewed at the highest level of abstraction, and most security breaches are at the software level. While still a problem, they can often be fixed by patching software. An increasing number of breaches occur at the hardware-software boundary or at the hardware level. They exploit the underlying complexity or flaws in hardware. Not only are they difficult to fix, they break security on all levels of abstractions above. You can't have a secure operating system if the hardware can be compromised. Hence, this is the area of focus at Tortuga Logic. A proactive security program is required to lower the risk and cost of security breaches. The security program spans collecting requirements through security verification all the way to handoff. And it's not just an engineering problem. It involves both internal and external stakeholders, for example, from R&D, legal, marketing, and standards bodies. While the concept of hardware security is easy, there are several challenges when implementing it in practice. The first challenge is to define and agree on security requirements for the system and communicating them among stakeholders. The second challenge is to translate security requirements to verifiable properties and applying them in an automated and scalable way during development. Thirdly, to identify security issues early, debug and remediate them before tape out to ensure requirements are validated. Tortuga Logic's Radix platform provides a complete verification solution for building a comprehensive hardware security methodology. Next, we will look at the steps including capturing security requirements, technology for security verification, and how Radix enables security sign-off. Hardware design starts with creating a functional requirement specification, followed by block and subsystem design and verification. Then the SoC is integrated and low-level software is tested. This is then followed by tape-out, manufacturing, and post-silicon testing. The hardware security program runs in parallel with functional design and verification and has similar steps. Each step interacts with the design flow and may require iterations as issues are identified. Security starts with threat modeling, which identify potential attackers, estimating what capabilities they have, how they may attack your design, and what benefit they may gain from compromising your system. Understanding the threats will help bound the security requirements and guide identifying, first, what are the assets and what are the consequences if they are not protected. Examples of assets in hardware designs include cryptographic keys, control and configuration registers, and memory storing code or user data. Example of consequences are user personal data being accessed or an attacker taking control of a self-driving car. Second, what are the security objectives for each of the assets? And third, what are the protection mechanisms required? For example, an interconnect firewall to enforce access permissions, and what is the attack surface or boundary that needs to be protected? For example, a JTAG interface or an over-the-air update channel. Security objectives for an asset is one of confidentiality, integrity, or availability. Confidentiality means that information in an asset is not accessible by unauthorized agents. Integrity means that an asset cannot be modified in any way by an unauthorized entity, potentially allowing a hacker to take control over the system. Availability means that the system works as expected, even when accessed by an unauthorized agent. For example, a denial of service attack by disabling features through control register access should not be possible. Performing threat modeling and creating security requirements can be challenging. One way to make the process more systematic and predictable is to leverage the Common Weakness Enumeration database, which is maintained by the MITRE Corporation. So how can the CWE help with creating security requirements? While each design is unique and the process of identifying assets require design knowledge, many designs share common hardware features such as memory mapped registers in peripherals, keys stored in one-time programmable memory, test and debug logic, etc. The categories in hardware CWE speak to what can go wrong with respect to common design elements and processes. If any of the categories in the taxonomy apply to your design, examining the entries in further detail will help identify what assets might be of value to an attacker and what the common consequences are for not protecting the assets. CWE also lists potential mitigations which provide insight when determining which protection mechanisms to implement. Moreover, many of the CWE entries highlight common security flaws introduced during the implementation of the defenses themselves. Security requirements are concerned with the flow of information between places in the design with different levels of trust. Security requirements identify security objectives for all assets, i.e., information leakage or information modification. The requirements are then translated to Radix rules which will be used during the security verification phase. Radix rules specify illegal information flows related to assets, and this makes it easy to write rules for both confidentiality and integrity objectives. Tortuga's Radix tool uses information flow analysis to automatically track secret assets through the design. It uses symbolic analysis to analyze information flows independent of data values, and it uses concrete control signals from simulation to enable or disable the information flow. Secret information needs to remain secret even if it is changed in the design, and Radix will track it through sequential and logical transformations. You don't have to know values, the path, or the latency for information flows in the design to create rules to run in Radix. This makes it easier and more expressive than using SVA or UVM. It leverages existing simulation and emulation environments and scales from block and subsystem level to SoC level, including running firmware on the SoC. A Radix rule specifies where information is not allowed to flow in the design. The security asset is either the source or the destination of the information flow. Information is tracked from a set of sources to a set of destinations, and will identify if any of the information from sources reach the destination signals. We will see several examples of Radix rules in the upcoming demo. Let's look at an example of how to develop a Radix rule for a simple example. In this case, we're concerned that an attacker can access encryption keys stored in eFuses. So the first step is to identify the secure asset, in this case, the eFuse key. Second, identify the attack surface or secure boundary where the attacker can access the device, in this case, the JTAG port. Thirdly, identify conditions when the assets need to be protected. Here, when the chip or the IP is in debug mode. Then we can express the requirement at a high level as the eFuse key must not be accessed via the JTAG when the DUT is in debug mode. And lastly, we identify the relevant RTL signals so that we can create the rules. Now that we have a Radix rule, how does it fit into the verification flow? First, we create a security monitor by reading the design RTL and the rule into Radix and compile it into a monitor, which is a piece of encrypted system Verilog code, which is then bound to the design using SVA bind when the design and the test bench are compiled and run. Any violations of the security requirements defined by the rules are reported in the simulation log and the waveform database. The violations are then debugged in the Radix GUI using the waveform database, and this will be shown further in the demo. The security monitor can also be used to verify security requirements when running hardware and software together in emulation. Scalability and reuse is critical for security. A security rule created at the block level is then reused as the block is integrated in the subsystem and the SoC level of the design, ensuring security vulnerabilities are not introduced in the process. I'll now hand over to Jagadish for the demo. Thank you.
Thank you, Anders, for discussing the increase in hardware vulnerabilities, the key components of a security verification program, the basics of information flow technology, and how Tortuga's tool Radix is used for security verification. I am Jagadish Nayak, a security applications engineer at Tortuga, and in the following slides, I will present how Radix is used to find two security vulnerabilities in an ARM SoC design. Let me first describe this design. This design is an SoC targeting IoT applications. It has an Arm Cortex-M3 processor, AHB interconnect that connects to flash memory and several SRAMs. There is an APB bridge to peripherals, for example, like a true random number generator, a real-time clock, and a UART. The processor supports software running in privileged and non-privileged modes, and it has an MPU or a memory protection unit to enforce access to certain areas of memory and peripherals that can be locked to prevent access from non-privileged software. What are some of the common mistakes that make secure assets vulnerable in a design? Let us look at two secure assets in this design. The true random number generator generates data that can be used to create cryptographic keys and should be accessed only by privileged software. The SRAM2 has a secure region in memory where privileged software stores data that must not be overwritten by user software. Here are some common mistakes that may allow access to these secure assets. System integration misconfigurations while connecting the blocks to create the subsystem is one. And second, user-level software accesses due to programming errors may allow user software to access unprivileged areas. Let us now look at the TRNG closely to track information flow of its secure assets. The information flow from and to the TRNG secure asset is governed by this policy. When running in privileged mode, the ARM core can read from and write to the TRNG. This is legal. When running in unprivileged mode, the ARM core cannot read or write to the TRNG. This is clearly illegal. Now that we have seen the information flow from the TRNG to and from the ARM core, let us look at the steps to create the security requirement. The first step is to identify the asset. This is the TRNG. The second step is to determine the security objective, which is confidentiality and integrity. Confidentiality because the ARM core should not be able to read information from the TRNG, and integrity because the ARM core should not be able to write into the TRNG in unprivileged mode. And finally, what is the protection mechanism that prevents this flow of information? The protection mechanism here is a lock bit which is set when in unprivileged mode to prevent the reading and writing of the TRNG by the ARM core. Now that we have determined the asset, the security objective, and the protection mechanism, let's write the security requirement in plain English. And this becomes the TRNG peripheral cannot be read or written in unprivileged mode. Now we convert the security requirement to an abstract security rule. This is created by taking into account the functionality of the design. Let's start by looking at the confidentiality rule. We have a label for the rule. Assert iFlow are keywords that I used when converting it to the Radix security rule. We have the source and the destination. In this case, the source is the TRNG, while the destination is the APB bus on which the information travels. The no-flow operator says that information from the source should not be read on the APB bus which travels to the ARM core. And the keyword is when we start tracking this information, which is in unprivileged mode. Hence, the confidentiality rule now reads as information from the TRNG when the system is in unprivileged mode should not flow to the APB bus where the ARM core can read it. Now the integrity rule. It has a label, and if you look at it closely, we find that the source and the destination from the confidentiality rule have now been interchanged. What this means is that the request, a write request specifically, from the ARM core should not flow to the random number generator block when we are in unprivileged mode. In our final step, we convert the abstract rule to the Radix security rule by instantiating the elements in the RTL. Let's look at the confidentiality rule. We have the label, then we have the source, which is the TRNG sample count register. The destination is the APB read bus. The no flow operator says that this TRNG register should not flow to the APB read bus, and this should not happen when we are in unprivileged mode. Let us now look at converting the integrity abstract rule to an integrity Radix security rule. We have the label TRNG-INT for the rule. The source is the APB write bus, while the destination is the sample count register. Note once again that the address, the destination, and the source have now been switched as opposed to the confidentiality rule. We want this write request to not influence the sample count register. The no flow operator says that, and we want to start tracking this information when we are in unprivileged mode. Revisiting the flow of Radix in the verification environment, we have now converted the security requirements to Radix security rules, and we're ready for the next steps of security monitor generation and compiling and running with the simulator. How do we generate the security monitor? We create a script with the following lines. We set up the project and give it a name. Then we read in the design files. Next, we set up the security monitor scope, and this tells the tool where to track the information flow in the design. Finally, we read in the security rules from the properties file, and we give the script to the Radix shell utility, which proceeds to create the security monitor. Once the security monitor is created, we compile and run with it. In this example, I will use VCS, which is a compiler and simulator from Synopsys, but the steps are the same when we run with simulator Exilium from Cadence or Questa from MITRE. So when we compile, we pass to the compilation command the security monitor files and where in the design to bind the security monitor files. Once the compilation is done, we run the simulation along with the test vectors. This completes the step of compiling and running with the security monitor. Again, revisiting the flow, we find that we've created the security rules and the security monitor. We've compiled and now run in a simulation. Once the simulation is done, we examine the log file output of the simulation run. Radix puts out messages that inform the user when the information is tracked and when it's failed. In this case, the rule has failed 8 times, and the rule times of failure are shown here. In this representation, I'm showing only 3 failures, but the log file is larger, and we can see that there are 8 failures. Once we know that there are failures running the security rule in the regression, we dump waveform data and we analyze the failure with the dump data. Radix has multiple analysis views that allow the user to track the flow of information from the design, isolate and fix the bug. The first view shown here is Path Viewer. Path Viewer tracks the flow of information in the hierarchy of the design from the source to the destination through time during the simulation. In this case, you can see that the source here is the sample count register, which was the source of the rule, while the destination that the information is not supposed to flow through to is the HR data S bus. And we can clearly see the path that the information took through the hierarchy of the design and the time through various nodes in the design. If you take the mouse button and click on any of the nodes shown in this design, it will show you the name of a node. Now, path view can be used to do a quick look and diagnose the problem. Here, we know that there is a protection mechanism bug because the read request from the ARM core should have been stopped by the TRNG decoder. So once again, path view will track the flow of information from the source to the destination through time in the hierarchy of the design, and is a tool that can show you a high-level view of the flow of information from the source to the destination. The next view is called the secure asset view. This view shows the failure, shaded in red, and the flow of secure information through the various blocks in the design in the hierarchy. This view gives the user a very good idea of in which blocks the information is flowing through. The red dot here signifies that there was information flow, secure information flow, in the block at the blue cursor, while the green dot tells the user that there was no secure information in that hierarchy or that module of the design. The secure asset view gives a high-level view of information flow through the blocks in the design hierarchy. It can be used to understand where information flows in the design. It can also be used to explore and find out more about the flow of your secure asset in your design. And finally, the third view is waveform view, which is used to debug and figure out exactly why this information leakage occurred. The source is the sample count register from the TRNG and is tracked. This is depicted by the red shade on the source in waveform view. We know we're running in unprivileged mode because the TDI signal is a 1. And we trace the flow of information by looking at the red shade in the various signals that lead to the destination here. The destination is HR data S, but the CCPR data bus, which was driving the HR data bus, is also red, which means that there was a flow of information from the source to the destination, and that is depicted by the failure that shows up with the little red line. Now, the lock bit that was supposed to prevent this from happening, the secure underscore I bit, is low, is a 0, which means that it was never turned on. So now we know why this information leaked through. In unprivileged mode, the lock bit was not set. Hence, waveform view will track the flow of information through the signals in your design, and it shades it in red. That gives a very easy visual cue for the designer or the verification engineer to quickly debug and look at where the error actually exists in the design. Having diagnosed from the waveform view that the secure I pin was a 0, let us now take a look at the code of the decoder to figure out why this was so. If you look at the code for the decoder block, we find that the output pcell underscore valid underscore 0 is dependent on secure underscore I as well as the p address underscore I signal. So the access to the TRNG is allowed by the decoder when the pcell valid 0 is a 1, and that drives the select pin of the TRNG block. Now, if we examine the code, the RTL code, we find that pcell valid 0 is a 1 if secure I was a 0, which means it was not locked, and that the P address was the address of the TRNG. So what's happened here is that the secure I has been incorrectly tied to 0 and should have been connected to the lock bit in a control register. Really, it should have been tied to this lock bit in the control register, which would be set to a 1 when it was running in unprivileged mode. Because it was not, the TRNG can now be accessed, which means read and written in all modes, including unprivileged mode. This is a common bug that we find in designs. The decoder block is a generic block and it's replicated multiple times. The only things that are changed are the address bus that are connected to the address pin and the lock bit, which is connected to various bits of registers. You also may have some blocks that are for which the lock bit is permanently tied to 0 because they're not secure. And that was the bug in this design, in which the secure asset TRNG, the lock bit of the decoder that selected the TRNG, was grounded, and thus the unprivileged software could access secure assets. Now that we have seen how to diagnose a security leakage in the TRNG asset, that was a hardware bug, let us look at another secure asset in this ARM design. The SRAM2 has secure memory regions, and let's examine the integrity information flow between the ARM core and the SRAM2 secure regions. In privileged mode, the ARM core can read and write into the secure regions of SRAM2. But in the unprivileged mode, the ARM core cannot write into the SRAM2. It can only read from the SRAM2. Thus, writing data into the SRAM2 in unprivileged mode is illegal. Now that we know how the information flows for the SRAM2, the integrity information flow, let's use the steps that we used in the first example to create the security requirements. Remember, we first identified the asset, and in this case it's the SRAM2. Next, we determine the security objective, which is integrity, which means that we're only now looking at the rule and saying that the ARM core should not be able to write into the SRAM2. What is the protection mechanism that makes sure that the SRAM2 can only be read and written in privileged mode but not in unprivileged mode? So here the firmware programs the memory protection unit for read-only access by unprivileged software when running in unprivileged mode. And now that we know those three key elements, we can create a security requirement, and that in plain English would be the SRAM2 protected range must not be written by unprivileged software. And the protection mechanism to make sure that that happens is that the MPU or the memory protection unit is programmed to allow no write access to the SRAM2 in unprivileged mode. Now that we have the security requirement for the integrity flow to the SRAM2, let us now write the abstract security rule. We have the rule label, we have the source and the destination. In this case, the source is the write transaction request from the ARM core, and the destination is the write request that is fed into the SRAM2. We want to make sure that the write request from the ARM core does not flow to the input of the SRAM2 write request. A couple of interesting keywords here now. We start tracking it when the request is made to an SRAM2, the secure address range, and we are running it in unprivileged mode. We also have an unless clause here, which says to ignore this request if the SRAM2 is not selected. So there are certain designs in which, and this one was one of them, in which the SRAM2 could be selected or could not be selected. So we want to make sure that when the SRAM2 is selected, then the write transaction from the ARM core cannot go into the SRAM2. The final step is to convert the Radix security rule and embellish it with RTL signals. So we have the abstract rule. We now convert it into a Radix security rule. We have the label. The source is the write access request from the CPU, and this time we now are using actual RTL signals. We start tracking the HWrite bus when the range is the SRAM2 address range, and we are running in unprivileged mode. The no-flow operator says that this write request should not get into the write enable pin of the SRAM2, and we ignore this if the SRAM2 is not selected. So now we have completely converted the Radix security rule to the RTL signals, and it looks very simple, but it takes the entire integrity property and converts it into a Radix rule that can now be run in simulation. Going back to our Radix flow diagram, I want to say that we have created our security rules, and I'm going to skip over the steps in which we've created the security monitor, the design RTL, and run in simulation, because the scripts were shown in the first example, and we pretty much run the same script, except that now we run it with a different rule. So we're going to look at the log file next after the simulation is run to check if there's any errors, and we find that the Radix rule has now failed at time shown here, and we're going to examine the dump data using the analysis views that I showed in the first example. Let us look at the waveform view of the dump data and analyze the failure. The write request HWrite-S goes high at the time shown. The SRAM2 address range a little later shows up. Now the write request is for the SRAM2 secure range. We are running in unprivileged mode, and we see that at that time the write signal gets shaded red, which means we have now started tracking it. And the write request gets driven onto the write enable bits of the SRAM2, which is our destination, and hence we signal a failure. This means that an unprivileged write request from the ARM core now flows to the secured SRAM2. Thus, once again, I want to emphasize that waveform view tracks the flow of information through the signals in the design, and it shades in red the secure information, and thus it makes it very easy to debug. So the question now is, why was this write request made to the SRAM2 even though the firmware programmed the memory protection unit to not send this request out of the CPU? So let's next examine the firmware. If you look at the firmware and the code wherein the regions are enabled based on certain conditions, we find that there was a bug in the firmware. And this region, this SRAM2 secure region, was given full access. And what that meant is that any privileged code that was running in the ARM core would be allowed to access this region, this secure region of the SRAM2. This should have been programmed as allowed to be read-only in non-privileged mode. So we go ahead, we fix the firmware, we recompile, and rerun our test. Note, in this case, the security monitor does not have to be recreated. All we have to do is change the firmware, the RTL is not changed, and we rerun our test to check if the fix worked for us or not. Let's look at the failing and the passing test now in waveform view in our Radix analysis tool. Remember, when the test failed, there was a failure shown by the red shading in the time bar. And we found that the HTrans2 request was made from the CPU to the HTrans bus. Now, if we examine the passing test with the fixed firmware, we find that we're still shading and tracking the HWrite-S, but now that request from the CPU does not translate into the HP trans bus. So now we have verified that after the firmware fix, the write request to SRAM2 is not made by the ARM core. Thus, I want to emphasize here that Radix can find firmware bugs that can affect the functionality of the hardware. I want to now do a quick summary of what I've shown in the demo. First, we want to talk about the Radix flow. It easily fits into existing simulation verification environments, and it's an automated and repeatable process. It's easy to write the rules. The Radix rules are completely capture security requirements. The Radix debug analysis views show you how information flows efficiently in your design and helps you quickly identify the root cause of the vulnerability. And then Radix detects security violations. As shown in the TRNG example, the first example, hardware incorrectly grounds the lock bit, thus allows access in unprivileged mode. In the SRAM2 example, we saw that firmware incorrectly programmed the MPU, and that allowed access to secure memory in unprivileged mode. These are very fundamental bugs that exist and can lead to security leakages and hardware security vulnerabilities. And finally, I want to say that these security bugs are hard to find using traditional functional verification tools. Hence, Radix is very focused on finding security bugs. It's easy to write the Radix rule. It's easy to analyze and find and fix security bugs. Thank you. And now for questions.
So I don't see any questions in the chat. So if anybody have a question, you can unmute and ask, and Jagadish or I can answer.
I was going to ask the audience if any of the examples resonated with their designs and some of the security concerns that they have, and do they have any difficulties in trying to find and fix and have decent coverage of the security vulnerabilities.
Hey, Jagadish.
Go ahead, Robin.
Hey, thanks. Just a quick question. I'm sorry, I did not listen to the entire presentation. Please bear with me if it is already covered. But how different is this tool from, let's say, any other formal validation tools? Let's say I'm from Intel, and at Intel we rely a lot on the Jasper Gold tool. For some of this sort of like security validation, where we want to protect an asset, and we write assertions like similar to what you had in your example, and then we try to prove it against this formal tool. So is it similar, or like what are the differences in terms of performance? And if you can elaborate on that, that would be helpful.
Yeah, so Anders, I think you should go ahead and answer this question.
I can take this. Yeah, it's a good question. If you work at the block level and fairly like small subsystems, the type of verification you do is pretty much the same. You could use Radix or formal at the block level. At the block level, the main difference is that for formal, you need to write constraints to basically model the environment so you don't get false violations. Radix is reusing the existing simulation environment, so there are no additional constraints. If you move up in size at the SoC level, running formal is very challenging, and if you start including firmware behaviors like we saw in the demo, that's not modeled in formal. So that's a major difference that we can with Radix you could model hardware software interactions.
Got it. Thanks. And is this commercially available, this tool?
Yes, it's it's available. It's got several customers as well. So
okay, excellent. Thank you so much.
Do we have any other questions?
So then I'm going to ask once again. Our tool is basically used across a wide range of products, right? It's used by large processor companies. It's used by companies that use hardware roots of trust. It's used by almost any company that has secure assets that they need to protect. They have security requirements. Does this compare to what you guys are working with nowadays, and what kinds of methods that you use? Do you think that this will add value to your verification arsenal? Is there something that you saw in the presentation here that you said, oh, this doesn't make sense, or something that you said that actually will help you? I think everybody's being a little shy today. What I'll do is Anders and I will hang out here for the next 10 to 12 minutes. And if you have any questions, definitely, please feel free to ask or type or in the chat. But one more thing, you can, after the session, you all can go to Gather Town, and we have representatives in the booth there. You all can talk one-on-one at that point too. Anders, maybe while we're waiting for questions to be asked, should we talk a little bit about the exploration of design that we can do using Radix, right? I know that you've worked with some clients recently where they've used Radix actually to find out where assets flow in the design. You want to talk a little bit about that?
Yeah, I could do that. So one problem in verification, regardless of if you're using formal or simulation, is that you're really only finding bugs that you're looking for. That the rules that Jagadish showed in the demo was that if the TRNG value could flow to the processor. So if we can verify that rule, we only verify that that information can't flow to the processor. So we're not looking for the unknown unknowns. That we didn't look for if it could flow to another memory. So we don't know if that's a problem. So with Radix, since we are tracking information flows in the design, we know where secret information or information about the secret assets are at all times. So we could use Radix to analyze and show where in the design can the information flow. And by reviewing that, a designer or verification engineer sees that it reaches an instance that was unexpected because of a misconnection or a design flaw, and then you can analyze that further. So by looking at the kind of visualization tools we have in Radix, you could see behaviors that are suspect that needs further investigation, but you didn't know ahead of time that you were going to look there. But by doing the analysis, you find out more about the security behavior in your design.
Yeah, I'm going to add to that, right? So designs usually are not all made from scratch, right? So there's a lot of third-party IP. There's a lot of blocks that were used in previous versions of the design that are kind of put together to make your new design. And sometimes what happens is that operations change, but when you implement them, some old code may be there left behind. So what Radix allows you to do is just say track an asset and say where does my asset actually flow when I run a simulation. You can run a couple of simulations, and then you can examine the dump data, and using this secure asset viewer, as I said, just look at where in the design or which blocks did my asset flow to. Two things I want to emphasize, right? We said information flow. So we really don't care about the value. The value could change from where it started. That's one thing. The other thing is that the information could be split into various different bits, or it could be broken up and chopped up and get into different areas of a design. Radix keeps track of all of those transformations and all of the bifurcations, if I may, where this information gets to. And then finally, it also remembers the source, right? So for example, if the information got and was stored into a cache for a very long time, and then it got out and got into a block where it should not have got into, we keep track of all of that. So it becomes a very, very efficient tool to kind of examine your design, to look at where information flows. and to basically track your secure assets, right? To kind of find out those unknown unknowns that Anders was referring to. So just one more facet of Radix that we wanted to put out here. There's one more thing I think probably we want to talk about, right, Anders, which is this concept of defining the security requirements, right? So we also have this methodology where we most times when you want to verify security for a design, you're stuck with a huge security spec, and the assets are kind of scattered all over the design. You don't know where to start and how to write your requirements. So it becomes very, very important that you have a spec which can be transferred into verification requirements. And so we have this methodology where you basically enumerate all the assets in your design. Once you find the assets, you then go back to the spec and say, should we be worried about confidentiality, or should we be worried about integrity for this asset? Once you have that, then you look at who can access it, who cannot access it, and what are the conditions. So once you have that little table with all your assets, the objectives, and the protection mechanism, the boundaries, then it becomes very easy to write the rule and then convert it to Radix rules. Now you can use that same rule and run it in formal too, which is fine. So that's another aspect. We have this methodology where it gives you a really nice comprehensive security requirement spec, which can then be translated into verification requirements. And then you can use that to kind of close your loop.
I see a question. Does the tool have any limitation on the size of design it can support? Can it be deployed at the entire IP subsystem level? So not really. If you can simulate the design, you can pretty much run Radix on the design as well, because we are just adding on or binding the security monitor to the design. So there isn't really any practical limitations on on a simulation. You get a little bit of simulation runtime overhead. If you're running an emulation, there'll be some additional logic, but we haven't run into any limitations where we couldn't run the design with Radix.
So Anders kind of hinted at this, but one of the use cases for Radix, and Radix has two tools: Radix S run in simulation and Radix M run in emulation. Most of our clients try to run Radix M with their security rules in emulation, because then you can run your firmware and your software, which might have bugs that put your design in such a condition where your security assets might leak. So these rules, you can construct them in simulation, and then you can run it on your larger design or your larger subsystem in emulation to make sure that your firmware does not expose any security paths when you run. And remember, the firmware that's run in emulation is kind of close to what you would implement in a finished silicon product. So there's that other advantage of Radix too, which you can run in larger subsystems with software and firmware. I think Are we getting close to end of time, Anders?
Yeah, it looks like we are at 12:30. Aiden, do you want to add anything, or are we being kicked out?
No, you can, if you still have questions, you can feel free to answer them, but if not, we can end whenever you're ready.
Yeah, I don't see any more questions in the chat, so feel free to contact Jagadish or myself. I added our email in the chat window, or stop by at our booth in the virtual exhibit if that's still open.
Right. Thank you for listening to our presentation, and we definitely would love to answer all your questions. Yeah.
Thank you.
Thank you.